All right, so we are back with set 17 and 18. I am just going to do one video for set 17 and 18. For the set, again, I'm going to just go through the work that I've already posted on Canvas. This is not my preferred method, but I ran out of time this week. So I just want to get something to assist you guys for your quizzes and your test. Your quizzes next week and your test, I think 2 weeks from now is the next test. Don't quote me on that. So again, I know that when I'm not writing, probably not as clear, not as in depth. If you need extra help, I have had students that have reached out and asked for help. I am more than happy to make time. You can meet me in my office. We can meet online. You can just send problems that you're having issues with and I can help you solve them. Please reach out if you need additional help. Okay, now I'll solve problems. All right, so our first problem in chapter 8. So we're going on to chapter 8. Chapter 8, we're looking at chapter 8, rotational equilibrium dynamics. We're looking at torque. Oh yeah, so I know a lot of you guys are mechanical engineers. This is right up your alley. Okay, so 4, find the net torque on the wheel in the figure below about the axis through O perpendicular to the page. Taking A equals 10 centimeters, so the radius of the inner circle is 10.0 centimeters or 0.1 meters, and B, the radius of the whole circle roll is 0.25 meters. All right, so as always, we're going to write down what we're looking for. We're looking for tau. We're going to write down what we know from the figure that we're given. So we've got a force going clockwise at the top of the wheel, 10 newtons. We have a force going straight down, still going clockwise, 9 newtons. We've got a force going counterclockwise on the inside of the wheel at 12 newtons. Guess I didn't draw newtons there. I should have. All right, so as always, we write down what we're looking for. We're looking for tau. We write down what we know. We know that theta is 30. And we know all of our radii, which I didn't write down. And we know all of our forces, which I didn't write down. You should always do that. Any problem that you solve, you want to start with, what are we looking for? And write down what we know. I screwed up on this problem. I rushed through it. I should have written down everything that we know. My bad. All right, so let's figure out what all of the forces, let's figure out what tau is on, we know what the forces are, what tau is in the clockwise direction, because there's 2 directions of spinning, clockwise and counterclockwise. So we know that tau equals R cross F. We're going to have the 2 forces, the 10 and the 9. So we're going to have R F sine degrees of whatever plus R F sine degrees of whatever. So when we say degrees of whatever, torque is perpendicular to our forces, meaning our degree is 90. So we end up with sine of 90, and that's 1. So what we end up with is tau equals RF in probably all of these problems. I know all the problems that professor gave us, And I would be willing to bet that this book doesn't give more difficult problems. Anyway, moving along, sine 90, they go away. So we plug in what we know, we've got our R values, and we end up with 4.75. So that is tau in the clockwise direction. All right, now let's figure out what tau is in the counterclockwise direction. This one I really struggled with. I thought, man, did I screw something up? Do I not understand torque? So they give us degrees of 90, but we don't, or degrees of 30 in the counterclockwise direction, but that doesn't matter. I think they just gave us that to throw you off. I'm not sure. So if you think of like a roller on the floor, you can either roll it clockwise or counterclockwise, and it doesn't matter if your hand starts at the bottom or if it starts at the top, it's the same. So I'm not sure why I think they gave us that to just throw us off. Anyway, so counterclockwise, we're going to have tau equals R cross F. We're going to have sine of 90 again. So we're going to end up with 0.1 times 12, and we're going to have 1.20. Here, we're going to decide what our positive and negative are, because they're going in opposite directions. I chose counterclockwise to be the negative direction. As long as you put counterclockwise or clockwise, doesn't matter. So I have negative 1.20 plus 3.40 equals 3.55. So your answer is tau equals 3.55 Newton meters in the clockwise direction. All right, 6. Moving right along. Well, this one's fun. A dental bracket exerts a horizontal force of 80.0 newtons on a tooth at point B in the figure below. What is the torque on the root of the tooth about point A? All right, so this was kind of a difficult, I don't know, the figure's kind of difficult to read. So I kind of drew it in a different way to figure it out. So here's my drawing. It's a little bit different than what the figure is. As always, we write down what we're looking for. We're looking for tau, and we write down what we're given. This problem, I wrote down what we're given. I did it right. So we've got theta equals 48.0 degrees. We've got our force at 80.0 N, and we've got our radius of 0.012 meters. All right, so we're going to look for torque, and we know that torque equals R cross F. We're going to have RF sine theta. Here, theta is, so if you look at our graph, if you look at how I've drawn it kind of as a graph. It's kind of different than the figure. Theta is not our angle. Our angle is from the horizontal, not from the vertical, because the force is coming at the horizontal. So our degrees is 90 minus 48. So our degrees is 42. So we plug in our values, we end up with 0.642265. So tau equals 6.42 times 10 to the negative Newton meters in the counterclockwise direction. I don't know, for some reason dental tooth ones just, ugh. Work on your teeth. Oh, this one's kind of fun. All right, so we got this girl laying on some scales. In exercise physiology studies, it is sometimes important to determine the location of a person's center of gravity. This can be done with the arrangement shown in the figure below. A light plank rests on two scales that read FG1 equals 38N and FG2 equals 320N. The scales are separated by a distance of 2.00 meters. How far from the woman's feet is her center of gravity? All right, so drawn our figure. I didn't draw the woman because that would have taken me forever. I just drew her as L. So we're looking for her center of, they call it center of gravity. COM is just what I always write, center of mass. So we've got L equals 2.00 meters. Oh, sorry, COM is what we need. COM equals question mark. We write down what we're given. L equals 2.00 meters. FG1 equals 380N. FG2 equals 320N. All right, so finding center of mass, our equation is going to be FG2 times the center of mass equals FG1 L minus her center of mass, because we're looking at how far from her feet up her center of mass is. So we're going to have L minus her center of feet. So we're going to rearrange our equation to solve for center of mass. And we're going to have COM equals FG1 times L over FG2 plus FG1. We were given all of those values, plug them in, and we get 1.0857. So her center of mass equals 1.09 meters from her feet. That was a fun one. All right, 27. This was not a fun one. I don't know why this one took me a while. Just couldn't, I don't know, grasp it, I guess. All right, so a uniform plank of length 2.0 meters and mass 30 kilograms is supported by 3 ropes as indicated by the blue vectors in the figure below. Find the tension in each rope when a 70 N person is D equals 0.500 meters from the left end. Okay, so we write down, I drew the little diagram. I drew a little stick person because I could never draw what they have in our book. We're looking for the tension, so we're looking for T1, T2, T3. We write down what we're given. We're given the mass of the plank. We're given the force of the man. We are given the length of the plank. We are given the distance that the man is from the beginning of the plank, and we are given the angle T1 makes with the horizontal. All right, so starting with T1, I think I screwed up T1 originally, why this was kind of difficult for me, because I was not thinking the mass of the plank and then the mass of the man from the distance of the plank. I think I kind of missed that. So anyway, this one took me a while. Even PhD students struggle with some of these problems. Okay, so T1, we're going to look at the force in the Y direction, starting at the origin, which we're saying is 0.5 meters from this man. We're gonna have torque negative y, and we're gonna have torque positive y. So I just have r cross f negative y, r cross f positive y. We were given most of these values. We're going to have 0.5 times 700 sine 90 plus 1 times 30 times 9.8, 0 gravity sine 90 equals 2.00 T1. T1 is our force, sine 40, because it's 40 degrees, not 90 on this one. And we end up with T1 equals 350 plus 290 over 2 sine 40. We use our calculator and we get T1 equals 501 N. Once I figured out T1, it kind of, then we were on a roll. All right, so T2. T2, we're going to do pretty much the same thing. We've got T2 equals 70N plus 294 minus T1 sine 40 equals 994 minus 501 T1, what we found above, times 0.64, and we end up with T2 equals 672N. All right, so for T3, we're going to have T3 equals cosine 40 this time, because we're looking in the x direction. We're going to get 501, what we found first, times cosine of 40 in our calculator, and we get 384 newtons. All right, Merry Christmas. That one's done. All right, now we're moving on to set 18. We're going to stay in the same chapter. We're just going to go fly through the book here to 35. We're looking at some big guy's leg, apparently. Again, I didn't draw. All right, so the large quadricep muscle in the upper leg terminates at its lower end in a tendon attached to the upper end of the tibia, as shown in the figure below. The forces on the lower leg when the leg is extended are modeled in the figure below, where T is the force of tension in the tendon, W is the force of gravity acting on the lower leg, and F is the force of gravity acting on the foot. Find T when the tendon is at an angle of 25.0 degrees with the tibia, assuming that W equals 30.0 N, F equals 12.N, and the leg is extended at an angle of theta equals 40.0 degrees with the vertical. Assume that the center of gravity of the lower leg is at its center and that the tendon attaches to the lower leg at a point 1/5 of the way down the leg. Okay, that is a mouthful. Holy cow. This problem is why a lot of students say I hate word problems. But it actually turns out to be a very simple problem. All right, so we start off with, what are we looking for? We're looking for T. So I have drawn their little picture of a big quadricep and a leg and whatever. I have just drawn a graph, and I've drawn all of our forces. And really what we've got is we've got the force of gravity that we are assuming for the leg is at the center. We've got, or I'm sorry, not the center, 1/5 of the way down the leg, they're saying. We have the foot having its own weight. And then we have the theta 1 and theta 2. Okay, so an L. All right, so we write down what we're given. We're given mg of the leg. And then we're given mg of the foot, and that was 12.5. Didn't write it. I don't want blue. Blue is for forces. All right, so here again, like we did in the last problem, we're going to say that r cross f in the negative direction equals r cross f positive direction. So in the negative direction, we are going to have L over 5, because it was 1/5 of L, they said. So the big word problem said 1/5 L times T, which is what we're looking for, sine theta 1. That equals L mg of the foot sine theta 2 plus, because we've got the foot and we've got the leg, 1/2. They said the center of gravity for that part of the leg was 1/2, was the center of gravity was 1/2 of the leg. So we have 1/2 L mgl sine 2. So we're going to rearrange this equation to solve for T. We end up with kind of a jumbled equation, but we are given all of these values. So it's really just like a plug and chug problem. We end up with T equals 5 times sine 40 times 12.4 plus 2 times 30 over 2 times sine of 25. We were given all of those values, so we get T equals 209 newtons. So this reading this problem is like, holy cow, where do I even start? You start with, what do I need? What am I given? What equations do I know? And this turned out to be a very simple problem. All right, moving along. I need to stop talking because, again, I'm making a huge video. Another merry-go-round. A 50-kilogram merry-go-round in the shape of a uniform solid horizontal disc of radius 1.50 meters is set in motion by wrapping a rope around the rim of the disc and pulling on the rope. What constant force must be exerted on the rope to bring the merry-go-round from rest to an angular speed of 0.5 revolutions per second in 2 seconds? Okay, so I've drawn a little diagram here. It's really just a circle, R and a force. And we've got the force, let's say in a counterclockwise direction. I put it at the top of the sphere or the uniform disc, but you can have the force in any direction so long as it's counterclockwise, as we talked about in the one problem that they gave us an angle that we didn't need. All right, so write down what we need. We're looking for force. What we're given mass is 150 kilograms. We're given R is 1.50, and we're given omega equals 0.5 revolutions per second. We know that we don't want to deal with revolutions per second. This is a physics class, not an engineering class. So we're going to just change it right away. If you see revolutions per second, don't even look at the rest of the problem, just change it to radians per second. So we're going to multiply 0.5 by 2 pi radian, and we get pi radians per second. And we get T equals 2.00 seconds. All right, so let's look at the equations that we know that might be useful and see if we can't push stuff together, because what constant force must be exerted on the rope to bring the merry-go-round from rest to an angular speed? Looking at what we're given, there's not an equation that we can just plug and chug. So let's write down what we know. We know that L equals R cross P. We know that L also equals I omega. So now we have R, P, L, I omega, but we're looking for force. So we have P equals mv. And we also know, we learned a couple chapters ago, P equals F delta T. Well, we were given delta T and we're looking for F. And we were given R to solve for P. So we can take all of these equations, almost all of these equations, and kind of shove them together and solve for P. So what we're going to do is we're going to take L equals R cross P, L equals I omega. We're going to make that R equals R cross P equals I omega. We know that P equals F delta T. We're going to stick that in for P, and we're going to have R cross F delta T equals I omega. We are going to write the equation, mix it up to solve for F. We're going to have I omega over RT. We know that I for a uniform solid disk is 1/2 mr squared. We have m, we have r squared, omega over r cross t. We're going to cross off r. We are going to stick in everything that we know, and we can solve this equation now. And we get 1.76.715, and oops, I forgot units. Always right, units. Holy cow, units are so important. F equals 177 newtons. I thought that was a fun one. All right, 42. A potter's wheel having a radius of 0.5 meters and a moment of inertia of 12 kilograms 12 kilograms meter squared is rotating freely at 50 revolutions per minute. We are going to find that at radians per second right away. The potter can set the wheel in 6.0 seconds by pressing a wet rag against the rim and exerting a radial inward force of 70 newtons. Find the effective coefficient of kinetic friction between the wheel and the wet rag. Okay, so this one I thought it's really important to write down a force diagram so that we get how these forces are working. So like sticking a hand against a wheel kind of thinks, well, that's kind of like a horizontal force, but it's not, it's pushing inward. But the kinetic friction is going to be opposite the motion of the wheel. So if the wheel is moving counterclockwise, the friction is going to be counterclockwise. All right, so write our little force diagram, and we're going to write always what we're looking for. We are looking for coefficient of friction. We're looking for mu. Write down what we know. We got R and we got I. So, we got omega, but we're going to change omega right away. Omega, 50 revolutions per minute. We're going to change that to radians per second, and we get 5 pi over 3 radians per second. In a video previously, I know that I had said, if you get a pi, leave it in the equation to the very end. It is very common that pi's end up canceling out. Don't stick in 3.4 and get decimals, and leave pi into the very end. All right, so they're talking about stopping the wheel, and they're giving us the time it takes. So our omega that, not I. Oh, no, that is I, sorry. So the omega that we're given is going to be omega I. That's our initial omega. So we're going to stop it. So our omega final is going to be 0. So we've got time, and we've got the force that she's pushing in on the wheel. So this one again is one where we don't have one equation that we can just stick in what we know. So that's why we write everything that we know so that we can go, okay, this is what we know. What equations can we write down with what we know? So we know that tau equals I alpha. We know that L equals I omega. We used that one in the previous problem. We know that alpha equals omega, delta omega over delta t. And we know that tau equals R cross F. All right, so let's solve for alpha. Alpha's in lots of these equations. We have delta omega, which is just omega I because omega F is 0 over 6 seconds, and you end up with 5 pi over 18. So we've got tau equals I alpha. We were given I, and we solved alpha. So now we have tau. Tau equals 10 pi over 3. Now let's solve the equation tau equals R cross F. We're given tau. We're given R. The force in this equation is going to be the friction force. And the friction force we know is going to be the force of the woman's hand times the coefficient of friction. So we can insert R cross F. The F is the FH, which we were given, and the mu that we're trying to find. So we end up with tau equals R cross F. I call this FH, F of the hand, mu F. We're going to rearrange this to solve for mu, and we get mu equals tau over RF. All of these we know. We solve for tau. We're given R, we're given F equals 10 pi over 3 times 0.5 times 70 equals 0.299999. Mu F equals 0.30. And that is our answer. Again, just want to say, I say this a lot over and over again. When we solve these problems, we write down what we know so that we can go, okay, we know this. What equations do we know with these things? So we have angular, we have omega, we have moment of inertia, we have radius. What equations can we use to solve this? And it turns out that we needed 4 equations to solve this. But we very quickly just kind of threw all of what we had in. It took me just, I don't know, once I had the equations out, which took maybe a minute, this was solved in a minute. And that's why we write what we know. So, okay, my little lecture's over. Lecture that I give a lot. All right, so that is set 17 and 18. I will be back next week with set 19, 20, 21, and 22. See you all later.